Today we are starting Chapter 3, Numerical Summaries of Center and Variation. We'll be looking at Section 3.1, Summaries for Symmetric Distributions. A numerical distribution can often be summarized with just two numbers, one to measure our center and one to measure our variability. There are several measures of center and variability that we'll learn about in this chapter, and the decision regarding which ones are best to use will depend on the shape of the distribution, and that is our responsibility as statisticians to make this decision. So in the previous chapter, we were asked to identify a typical value of a distribution without doing any calculations, and as a result, I'm sure you saw that some of your answers were subjective. Today we are going to learn how to quantify our answers. So looking at this data set, which contains 9 Boston Red Sox players in 2015, the age of the Red Sox players, what is a typical age for following Red Sox players? So just looking at the data as we did in the previous chapter, we might say somewhere in here, I'm thinking maybe around 27. And will everyone have the same answer? Not necessarily, because we are just subjectively looking at this. So we need a method that everyone can arrive at the same answer when we're talking about a measure of center. And one measure of center, the first one we're introducing, is the mean, okay, or the arithmetic average of the distribution. The mean is a numerical summary that measures the center of the distribution and can be thought of as a balance point or center of mass for the distribution. So our formula given below here is for the mean, and we use this symbol that we say it's X bar. That's our sample mean. We'll be seeing a lot of that from here on. And then we are looking at the summation notation that tells us that we're going to be adding up all of our data points and dividing by the total number of data points. And this is the formula for calculating an average. So we're going to use the formula to calculate the mean age of the Red Sox players. So we would have to add them all up, 31 plus 23 plus 22 plus, and we keep adding all of them up, plus 28, which you can pause the video and give this a try. There's a total of 9 ages we're looking at, and this total would be 243 over 9, which gives us the mean of 27. So our sample mean, which we'd call X bar, is equal to 27. Now, let's take a closer look at why the mean is thought of as a balancing point. So let's mark this mean on our dot plot. So here's my mean right here. That's X bar equals 27. And we can see, why is this the balancing point? So what's the distance of each player's age from their mean? So if we look over here, this at 22, we have 2 players. The distance from the mean there is 5. And we could say that it's actually -5 to denote that it's below the mean. So we have 2 players whose distance is -5, whose deviation, we could say, from the mean. Here it's -4. This one would be -2. Then we have some players who are above the mean. This was one year above the mean, 2 years above the mean. This one is 4 years. We have 2 players that are 4 years and 1 player that's 5 years. So These are the distances that they're above the mean or below the mean. And when we include the positive and negative signs, as I did, we're really talking about deviation. So a negative deviation indicates that the age is less than the mean, and a positive deviation indicates the age is greater than mean. And when we add up these deviations, and you can pause the video again to take a moment to add these up, -5 plus -5 plus -4, you find that the deviations sum to 0. Okay, we'll look a little bit further into that later in the video. Now let's calculate the mean age of the following Red Sox player. But notice we now have a 10th player included in our data set whose age is 40. We can see this age out here on our dot plot. And so again, take a moment, pause the video, and calculate your X bar. Okay, so our X bar, we would sum all of our ages. Our sum will now be 283. We have 10 players and our mean is 28.3. So our mean has now shifted to here. So it's moved a little bit bigger than it was in the previous example. And what this tells us, this shows us that the mean is not resistant to outliers. Not resistant. That means that the mean is affected by the size of outliers. So if you have a data point that's really far away from everybody else, it pulls the mean toward it. And so when we don't have a symmetric data set and we have a skewed data set, the mean is not a good measure of center. So the mean is most useful with symmetric data sets. So the following distribution contains the ACT scores for one class of students at a junior high. Notice that the mean ACT score, X bar, is equal to 24.6, is roughly in the middle of the distribution, is marked by the triangle on the horizontal axis. Do you think that 24.6 accurately represents a typical score for these students? Yes, it looks pretty good. Our shape of our distribution, we would say, is roughly symmetric. And we would probably identify the this 24.6 to be the center of our distribution. The following distribution contains salaries for professional baseball players in 2010. It's in millions of dollars. The mean salary in 2010 was X bar is equal to 3.2 million and is marked on the triangle by the triangle on the horizontal axis. So notice now that this is where our mean is. And given that 70% or almost 70% of the players made less than the mean, we might not think that this actually is a typical salary, right? So what would be a more accurate salary for these players? Probably something more over in this ballpark. And when we look at the shape of this distribution, how would we describe it? We would say that it's symmetric, it's skewed right. And so notice that the mean gets pulled towards the tail. So the mean is not a good not a good measurement to use when we have a skewed data set. It gives us an accurate idea of a typical value in a symmetric data set, but not when the distribution is skewed. We will consider another measure of center that gives us a more accurate typical value for skewed distributions in the next class. So here, this is a note, but it's very important. Technology will always calculate the mean for you, even when it's not the appropriate measure to be using. So it's up to you as the statistician, it's your job to decide whether to use it. And always start with a picture. And likewise, you as a consumer or reading a journal article should be cautious of when people are using mean, and should look at the picture to see if they're using it in an appropriate manner. So calculating the mean by hand is fairly easy if you have a small data set, but tedious for larger data sets, and we tend to use technology for calculations when we have a large data set. But before you do that, remember to always create a visual display to determine whether the mean is an appropriate measure. Is the mean enough to describe a distribution? No, not usually. We also want to talk about the spread. Consider the following information given in the text concerning American women. The average height of American women is 5'4", and the average height of the American fashion model is 5'11". Are these two means enough to compare the distributions of American women to American female fashion models? Probably not, since we don't take into account variation that exists in these two groups. Which group do you think would have more variation? So likely the average American female group would have more variation. The model group would probably have less variation, since most models are probably centered around that 5'11". The heights of women in these two distributions most likely do vary, and we can measure this variation informally by the horizontal spread of the distribution. Okay, so the most basic measure of spread is called range, and that's just calculated by subtracting your maximum value minus your minimum value. So which group of American women do you think has a larger range? Probably the group that's just American women, not the fashion models. Although the range is easy to calculate, it only relies on two data values, your maximum data value and your minimum data value. And it's not very descriptive of the entire set. It's very dependent. If you have an outlier, it may be misleading. So because of this, we need a better way to measure variability. If we're interested in describing a typical value in a distribution, we should also describe how much variation exists. And these two measures, a measure of center and a measure of spread, can help us understand whether most observations are close to a typical value or far away from it. The following two histograms on page 89 of your text show the daily high temperatures in degrees Fahrenheit recorded over 1 year in Provo, Utah, and in San Francisco, California. So first, let's describe the shape and center of these two distributions. So we have Provo and San Francisco. Probably the center of Provo, just visually looking at it, would be somewhere around here, maybe around 65. Just kind of visualizing it. And the San Francisco, probably also maybe 65, 70 area. So Provo centers around 65, and San Francisco centers around 70-ish. The distribution shape, these are a little bit tougher. I wouldn't say, we might say that Provo is fairly symmetric. It's not symmetric, but it's not skewed either. And same for San Francisco, we might say it's fairly symmetric. And then we also might be interested in how spread out their temperatures are. And so it looks like Provo has a larger spread. And San Francisco has a smaller spread. So which city has a greater range in their daily high temperatures? Range is your max minus your min. We don't have our data, but we could at least give an about here. So Provo looks like their max is around maybe 105, and their min may be at 25. So their range is about 80 degrees. San Francisco, max is 95-ish, around there, and min might be 50. So their range is about 45. Another measure of spread is the standard deviation. And we will be really using this really for the rest of the semester. A standard deviation is a numerical summary that measures the spread of the distribution by calculating the typical distance of the observations from their mean. Which do we think would have the greater standard deviation? And Provo, because their temperatures are spread out more. So a typical distance from the mean would be greater than that in the San Francisco data set. So the formula for standard deviation looks like this, where S is our sample standard deviation. It may look a little messy, but we can just think about this as a list of instructions. And we are going to go through and calculate this together once, because it's good to see how this all works. But typically, we're going to be doing this using technology. Okay, but first let's go through and look at it. So S is the symbol for a standard sample standard deviation. We have it's equal to, we have a big square root sign. We've seen this summation sign before in the mean, so we're going to be adding up a bunch of stuff. All this stuff in parentheses is going to be added, and then we'll be squaring it. We'll be talking about this in a minute down below. Remember the X would be our data, and our X bar is our sample mean, and it's all over n minus 1, where n is the sample size. So let's go through and calculate one together. Step 1 says to calculate the mean age. So we have, if you count up the number of data points we have, our n is equal to 17. You can pause the video for a second and go ahead and calculate your mean age. So to calculate the mean age, you should have added up all the ages and divided by 17, and your mean would be X bar would equal 16. The first column here, the second column here is the deviation from the mean. So we're looking at the data point. So in row 2, we're looking at 14 and how far away it is from our mean of 16. And we have it that it's -2. In other words, it's 2 away, but it's below the mean. Again, pause the video, and I am going to fill in the rest of this chart. Okay, our deviations from the mean have been filled in, and if we sum these up, we'd see that our sum is 0 for these. Next, we're going to be looking at the squared deviation. So we're going to take what's ever in column 2 and square it. We have to be careful to notice that we're squaring negative numbers, which gives us a positive number. So again, I'm going to pause and fill in the rest of this. And now we can sum up this column, and then we get 40 is the sum of our squared deviations. Okay, so at this point, we've done several steps to our formula. We are still looking at, we're going to take the square root and the sum of all the square deviations, that's our numerator inside the square root. And the next step is to divide it by n minus 1. Our n is 17. So we would get 40 divided by 16, and then we take the square root of our result, and that gives us 1.58. So the typical age is, on average, 1.58 years away from our mean of 16. So it says, go back and look at number 21 and find the sum of deviations from the mean. We did that earlier. And why do we think that when we add up all the deviations from the mean, the sum of them, why do you think the sum is always turning out to be 0? So we just saw that in our last problem too, and it's that the negative deviations cancel out our positive deviations. Because the mean is the center of our data set. By the way, the variance, which is another measure of spread, is s squared. In other words, it's similar to the standard deviation, but we're not taking the square root. So s squared is used to talk about the sample variance. And what do you think the units for variance are? And they would be our unit squared. So in this last example, it would have been years squared. And so standard deviation is often used because we're talking about the right unit. We're still in years when we're talking standard deviation. All right, and let's look at number 24. The following histogram contains the hypothetical ages from this last data set. Let's take a closer look at the standard deviation, s equals 1.58 years. And what is meant by the typical distance of the observations from their mean. So remember, the standard deviation is the average distance from the mean for a data set. And so 1.5, the mean is at 16. So 1.5, I'm going to change to red, is about from here and here. So this is one standard deviation on either side of the mean. And you can see that most observations fall within one standard deviation. And then if we went out even further, so maybe about 2 standard deviations, maybe here actually. So you can see that most or almost all of our observations fall within 2 standard deviations. So this is a typical distance from the mean. That's what the standard deviation is.